Okay, we're continuing on here. 14? Chapter 14. That sounds good. All right, so we're knee deep into titrations. Yes. So we already talked about last time a couple types of titrations. We got strong acid, strong base titrations. You got a wonderful titration curve, looks something like that. Yeah, it's not bad. And again, in this case, we are adding the base to the acid here. We do see obviously our increase in pH as we continue through the titration. We get to our equivalence point there. As we talked about, we see a fairly vertical leap to the equivalence point. And that is typical in a titration curve. And then obviously we curve out after they're past the equivalence point. And in this type of titration, again, like all titration curves, there's really four parts. There's kind of before you begin, before the equivalence point, at the equivalence point, and after the equivalence point. And again, in this type of titration, if we're looking for the pH, obviously before you begin the titration, all you have is a strong acid, which means you can directly go into the pH equation using the molarity of the strong acid because you haven't added anything at this point to get kind of your opening pH, if you will. As you start the titration, as we talked about, obviously we do need to do an ice table here. And as we talked about, we do need to do an ice table in moles. And really the purpose of this is you will have enough of your strong acid at this point to use up any base that you put in there. So the purpose of this ice table is to really end up with the concentration of your strong acid at the end. And after you do that first ice table in moles, as we talked about, it's a good idea to convert it back into molarity using the total volume. And that would be obviously the volume of the acid you started with and the volume of base that you added to get wherever you're at that point. Once you do that, you still have really the concentration of a strong acid, which means you could then go into your pH equation at that point. Once we reach the equivalence point, which is the point in the titration where we have basically equal moles of acid and base, pretty much the only thing that you'll have left over at this point in the titration is a salt. And since that salt did come from a strong acid and a strong base, that should be a neutral salt. And that should really give you an equivalence point around a pH of 7 there. Because again, for example, sodium chloride may be the only salt that you have left there at the equivalence point. As you go past the equivalence point here in this titration, once again, does require an ice table. And again, it does need to be done in moles. And at this point, what happens is you're basically just dumping excess amount of base into your beaker at this point because that pink color didn't stop you from stopping the titration. You said, why not? I want the whole curve. I don't want my curve not to look good on top there. I want the whole curve all the way there. And really at this point, the purpose of the ice table is actually to figure out how much of your strong base you have left over at this point. So again, the idea of this guy is to figure out your strong base you got left over that you just keep on adding. You want to convert it back to molarity at that point. And remember though, because it is a base, that is going to get you the pOH first, and then you got to get yourself again to the pH. So really anywhere along the line here, you should be able to calculate the pH. And again, those are the four sort of important parts in this type of titration. We then talked about really another type of titration where we finished up on last time, which was a weak acid, and very much like the titration you did in the lab as well, strong base titration. And once again, here we're adding the base to the acid from the burette, and we get another lovely titration curve, professionally drawn right there. And we got our equivalence point sort of happening here. And we see the same sort of rise to the equivalence point, and afterwards we have the same four spots along the way here before we start titration, before the equivalence point, at the equivalence point there, and then past the equivalence point. And once again, it is a little different, this titration, in terms of how you get to the pH based on what we're dealing with. So First off, obviously at the beginning, before you start the titration, really the only thing you got left there in your beaker or to start with is a weak acid, which basically means you do need to do an ice table. You could do this guy in molarity using the Ka value. You're going to go through a normal sort of ice table weak acid type problem at the beginning here. You're going to solve for X. X is going to equal, thank you, the H plus concentration. And then that will allow you to get yourself really to the pH. So again, you can try an assumption to see if it works or not, but you do need to kind of solve it at some point. Once we start this titration from the first drop there to the equivalence point, it will require at least one ice table. Also, once again here, done in moles. And what you're going to hit pretty much always in this type of titration at this point is a buffer. So you'll be left with a buffer at the end of that ice table. Probably should roll yourself into some molarity as well. And again, you do have an option at this point. You can either do a second table or probably a Henderson-Hasselbalch would be a great move, probably right about here. Yeah, would be where you would want to do it. So you could go into the Henderson-Hasselbalch because again, it is a buffer, and that's where we could use that. Should be probably an acidic buffer here. And as we talked about, once you kind of blow through that buffer, you are going to get that vertical leap to the equivalence point. Once again, at the equivalence point in this situation, you will again be left with a salt, and you will need to do an ice table in moles. And that is essentially what you'll be left with at that point. You want to convert back to molarity, and you will need to do a second ice table. And this will be a hydrolysis type of ice table. And that is because that salt did come from a weak acid, which means it will react with water. And it's going to react as a base, which means it's going to grab off at H plus from water. That's going to produce some hydroxide. And that's why we expect in this type of titration our equivalence point to be basic, because we have that salt basically producing hydroxide at this point. And once you go past the equivalence point there, we need to do an ice table again in moles. The purpose of this is very much like the purpose of the other titration. At this point, you're just dumping sodium hydroxide, for example, or base into your solution. So the purpose of this is to get the concentration of your strong base left over. And once you have the concentration of your strong base, once again, that could get you to your POH and then obviously to your pH in that case. Questions on that there? All right. So we were looking, I think, at this one right here last time when we finished up. So why don't we just do a quick little example of this one? What is the pH after? Oh, let's go with 21 milliliters of 0.1 molar sodium hydroxide is added to 25 milliliters of 0.1 molar acetic acid, right? I'll go with that. Ka value for acetic acid. Everybody's favorite number, 1.8 times 10 to the minus 5. Yeah. All right, so give it a go. I'll do it as well. Here, we've obviously started titration, so I'm going to need some moles, and we'll do some moles here of our sodium hydroxide. We do need to convert our volume into liters here. We're going to times it by our molarity, which is 0.1 moles per liter. And that's going to get us 0.0021 moles of sodium hydroxide. We'll do the same thing for our acetic acid here. And we have 25 milliliters converted into liters times by the molarity of 0.1 moles per liter. Gonna get us here 0.0025 moles. All right, so we'll do our ice table, which we definitely need. So a little bit of acetic acid plus some sodium hydroxide here. Gonna do a little double displacement reaction. Gonna make some sodium acetate and some water in this case. So initially here, 0.0025 moles, 0.0021 moles, and a 0. Obviously, at this point, we should know where we're at. We are before, at, or after the equivalence point. We are before. Once again, this is what we're adding. This is what we started with, and we obviously have less moles of what we're adding than what we started with, which tells us we are definitely before the equivalence point. That means you should really know what we end up with here. So let's see if it is what you think. The change here should be our sodium hydroxide. And that means when we reach equilibrium, 0.0004 moles. We got 0 and 0.0021 moles. At this point, we're going to just turn it back into molarity, which, as we've talked about, is a really good idea. We had 25 mils of our acid to start with, 21 mils of our base we added, 46 mils, it looks like. So we'll divide this by 0.046 liters each of these. And that's going to get me something here with some numbers. Looks like maybe 0.008. I'll call it 70. And 0.0021 divided by 0.046. Looks like 0.0457 molar there. I got that right there. All right, this is, if you're not sure, we have sodium acetate, we have acetic acid left over, and that is a buffer, right? Which hopefully you should have expected based on where we are in this titration. We are in here, right? So we can go right into really our Henderson-Hasselbalch in this case, or you can do a second table, but I'm just going to go this way with it. Here are pKa minus the log of 1.8 times 10 to the minus 5, 4.74, giving us a pH is equal to pKa. We do want to go with our base, which is our sodium acetate, 0.0457 divided by my 0.00870, I guess. And we're going to get something. Let's see. Take that, maybe divided by that. Do a little log action. And a 4.74. And that gets us something like 5.46 as our pH, which on this particular titration does fall between those numbers. So hopefully I didn't mess it up. Any questions on that there? Again, you could have done, like we talked about, a second ice table. Instead of the Henderson-Hasselbalch, you'd probably want to do like a acetic acid dissociation with a Ka of it. And again, you got to make sure you got an initial on the product side if you want that route. Yeah. Equivalence, yeah. Say it one more time. Why is it not? Right. Right.
And it wasn't like less than.
Because we started with we started with, in the beaker in this case, the acid, right? And we're adding the sodium hydroxide. So that sodium hydroxide at this point, because we are before the equivalence point, is like the limiting reagent. There's less moles of it. So basically when it reacts with It's kind of like this. So this is like the acetic acid, and this is like the sodium hydroxide. So there's more moles of acetic acid. So when you add that base, there's plenty of it to react with it. And it's going to use it all up. It's in excess, basically, the acetic acid. It's not until you get after the equivalence point, where at the equivalence point they're equal. But when you get after the equivalence point, you start adding more sodium hydroxide. Now you got way too much sodium hydroxide, not enough of acetic acid to handle all that. And that's why the acetic acid gets chewed up after the equivalence point. No. Other questions? So essentially in all titrations, up to the equivalence point, pretty much the change is always going to be whatever you're adding, because it's always going to be the limiting reagent until you hit that kind of equivalence point. And then once you go past the equivalence point, it switches around. What you started with, it becomes the limiting reagent, and what you're adding is the excess. Other questions? Yeah. All right. Feel like we have another titration curve. There it is. Look at that. All right, that's an upside down titration curve. Just turn it this way. Turn straighten it. All right, so last titration here we're going to talk about is a titration of a strong acid with a weak base. So something like a little NH3, which is a weak base, plus a strong acid like hydrochloric acid, will get you ammonium fluoride. And I'm actually going to separate them. You can, if you like, leave them together as ammonium fluoride as one thing. But I'm going to separate it for reasons we'll understand as we go through our talk here. But you can also obviously just write the product as this as well. So that's essentially the same thing. Now, in this titration, it is a little bit different. We actually have up in the burette the HCl. So we actually have the acid up there. And we're dropping acid in this case into our base down here in our beaker. So previously we're dropping base, here we're dropping some acid, and we're going to add that here to our base. So that's why our titration curve looks upside down, because we are starting with base, which means we have a higher pH. And as we start adding the acid, we start to see our pH start to drop and become more acidic. We actually see kind of a similar thing as we get to our equivalence point. We see still a vertical drop in this case instead of a rise in the pH to the equivalence point and along the way. Still, believe it or not, the same 4 parts to this titration curve that we've been talking about. If I knew how to count, that would be 3 next. There we go. That is 4. It's hard sometimes on Thursdays. So 1, 2, 3, and 4 here. So we're going to talk about each of these points along the way and how we calculate our pH. So let's just start with the first part there, which is before we add any acid in this case. So before really the titration begins, really the only thing that we got left are really starting with in our beaker is our weak base. And since this is a weak base, if we want the pH, I'm going to assume that we probably should do like a KB type problem, a nice weak base problem, since that's the only thing we got. So that's going to be something like some ammonia, a little bit of water. Since that is a base, it's going to accept that H plus. It's going to form NH4 plus and a little hydroxide, hence it's a base. This is going to be just a normal table in molarity because we haven't added any volume, so you could just lay up the regular molarity here. These will be zeros, and our favorite things, X's along the way here. Molarity minus X, X, and X. Since this is a base, we would go into our KB expression in this case. We would solve for X. A reminder though, in this case, when we solve for X, X does not equal the H plus concentration. It equals the OH minus concentration. So that's going to equal the OH minus concentration. That's going to get you to your POH and hopefully to your pH at that point. Obviously, at this point, it should be basic as you start out since it is a base, right? So you should have a basic pH. So kind of very similar to the previous titration where we started with a weak acid. We do kind of like a Ka problem, just a basic weak acid problem. Here, because we're starting with a weak base, you just do a basic weak base type problem with an ice table. Any questions on that? All right, then let's talk about what happens as we start dropping that acid all the way down to before the equivalence point. And at this point, much like the other titrations, we will need an ice table because we are going to obviously have a reaction between those two things. So before the equivalence point here, we'll have our reaction of our NH3. We're going to drop some HCl in there. It's going to do a little reaction type of deal. And we're going to get a little NH4 plus. And really here we will get some chloride as well. And once again, as I mentioned earlier, you could keep it together if you want, or you can separate it like I did here. And we're going to do this ice table in moles like we did other ice tables. And again, I'm just going to make up this number like I've been doing on our previous example. So we'll start with 4 moles here of NH3. This is what we're adding, which is my HCl. So as we talked about previously, if I am before the equivalence point, the moles of HCl should be less than, equal to, or greater than 4 in my example. Should be less than, so why not go with 2? Seems like a nice number. And we'll go 0. Change here, as we were just talking about a second ago, we are before the equivalence point. So whatever we're adding is really less moles, as you can see from the table, than what we started with. So it is the limiting reagent, and that would be the change here. And at equilibrium here, we would end up with 2 moles of this guy, 0 of this guy, and 2 moles of this guy. By the way, why am I ignoring this guy? Yeah, it's neutral, so best maybe not to put numbers there that you don't really need to use so you don't screw it up, right? So again, that's why I sort of ignore it. At this point, we're good chemistry students, so we'll just convert this thing back into molarity so we don't have any headaches later on in our calculations. And again, obviously we'd be using the total volume in the titration at this point. If you're not sure what's going on at this point, again, you can look at your ice table to sort of help you out. We got this guy left over basically, and we got that guy left over. Are those things related to each other? I'm going to say yes, they are related to each other. They're related to each other as a buffer. Yeah, that is a weak base and its conjugate acid. So very much like the previous titration, once again, we hit buffer territory here as we kind of open up the titration. And because of that, heck, why not? Let's do a little Henderson-Hasselbalch at that point to get to our pH. You do got to be careful about a couple things, probably. You probably have, in this case, the KB, which you have a couple of options. You could use KW to turn that into a KA, to turn that into a pKa, or you can turn that into a pKb, take 14 minus the pKb and get the pKa. So you could also go that route as well, and you can put your pKa in here. You also want to make sure you get the base, which in this case is the ammonia, over the acid, which would be the ammonia. Yes. You could. So you could use that one that we saw earlier. You could also use the one that we talked about, which is the pKb plus the log. You got to be careful because that is acid over base if you use that one. Again, as we talked about previously, most of the time, especially if you're making a titration curve, you probably want the pH. So might as well just go straight into that without confusing yourself and maybe thinking you are getting the pH there instead of for pOH, but you absolutely could use that one as well. Yeah. So any questions on that? So we will hit a buffer. This is going to be mostly a basic buffer here, as you can see, all the way through there until obviously we blow through the buffer here, and that's going to drop us pretty quickly because at that point we're adding a lot of H plus kind of quickly at that point of the titration. So we see that big kind of drop in the pH there to the equivalence point, followed by it continuing to drop afterwards. Now, if we get to step number 3 here in our titration curve, which is the equivalence point, once again, we are going to do our reaction here of NH3 plus our HCl. Gonna give us, once again, NH4 plus and Cl minus. And again, you could keep them together. It really is your call. Again, we're going to start with my 4 moles of what I'm starting with here. And since I'm adding this and it is the equivalence point, we know for sure it needs to be equal moles. So we should have 4 moles of our HCl at this point, because again, that's really the definition there of the equivalence point. Once again, you hopefully cannot choose the wrong number, since 4 is the only one kind of staring back at you. So that would be 4. That would be 4. This would be plus 4. At equilibrium, 0, 0, and 4. Once again, we can convert this back into molarity. So as we would expect, we have none of the base or acid that we kind of started the reaction with at the equivalence point. We are left with just a salt, and really the salt here is the ammonium chloride, which I've already separated out in this case. And we've already determined earlier that that's not going to do anything, as that is neutral. What about this guy? Will it do anything? It will, because it does come from NH3, which is a weak base, which means it will go through hydrolysis. So once again here, we are going to end up at the equivalence point, much like the last one, where we will have a salt that will go through hydrolysis with some water. Once again, because this comes from a base, this would technically be the conjugate acid. And because that's the conjugate acid, it will act like an acid when it reacts with water, and it will donate over the H plus. The result of that is you will always get where it came from, which is NH3, and we will make a little H3O plus. So we would expect the equivalence point to be acidic, basic, or neutral. We would expect it to be acidic at this point. And we also should use what in our calculation? A K? A, yeah. So once again, you probably have only the KB given to you in this case. So a little KW action there to convert it over into a KA, like we just talked about. At this point, we are going to initially start with our equilibrium concentration. So that's really the purpose of that first table, is to get the equilibrium concentration of the salt. And this table, which is in molarity, well, goes back to some zeros and X's along the way. This, obviously, as we just talked about, will go not into the KB, but into the Ka expression. That's where we're going to solve for X. And actually, in this case, X does equal the H plus concentration. And that means we could go actually right into our pH at that point. So super identical to the previous titration curve, except it's upside down. We also hit a salt here at hydrolysis that will go through hydrolysis. It will always be acidic at this point, because that salt always comes from a weak base. So that weak base will always produce a salt that's basically going to act as an acid and going to donate it over to the water to produce H3O plus. And that is why we would expect the equivalence point in this titration to be acidic. So if you think about the equivalence point in 3 titrations we talked about, strong acid, strong base, we expect to be neutral because we have a neutral salt. Weak acid, strong base, we expect it to be basic because we have a salt that goes through hydrolysis and produces hydroxide. And here in this titration, we expect the equivalence point to be acidic because we are producing a salt that comes from a weak base that will basically produce H3O plus. Any questions on that there? All right, so where you're dropping down here to our equivalence point, we're continuously dropping at this point, and it's really because at this point you're now adding a lot more just free strong acid into our buffer, our real not really buffer, but into our titration here. and you're just dumping a bunch of H plus in there. So in the past the equivalence point part of our journey here, we would expect a little bit more acidicness happening here. So past the equivalence point, once again, we will have our reaction in this example. Again, we're starting with this guy, we're adding this guy. So we'll start with our 4 moles here. And again, that we know that it is past the equivalence point, we should have obviously more moles of what we're adding. So we'll go with 6 on the made up number scale and 0. This, as we were also talking about a little bit earlier, because we are now past the equivalence point and you are not stopping your titration, you're just letting it drop in there. You now have an excess amount of what you're adding and less amount of moles of what you started with. So again, there's that switch we were talking about. Actually, the HCl in this case is going to be the excess reagent, and this is going to be your limiting reagent. So as we talked about, also just logically speaking, as we talked about, always choose the smaller number. Yeah. So in this case, we will take the HCl, not the HCl, the Na, the whatever that is there, NH3, I suppose. That thing right there, well, that's what we're going to take. We're going to go 0, little 2 moles, and 4 moles. We're going to convert ourselves back into molarity. We're using our total volume. Once again, at this point, we got this guy and we got this guy. Is it a buffer at this point? It is not. So once again, a cautionary reminder, do not use the Henderson-Hasselbalch in places you should not use it. And this definitely is a place you should not use it. We have basically 2 things that are not a buffer. We have this guy, which is clearly our salt that will go through hydrolysis and act as an acid, an acidic salt, basically. And we have this guy, which is a strong acid. So much like in the previous titration, between the two, that guy is not going to contribute as much as the HCl will, because again, the HCl just needs to go for a swim and it's going to produce a bunch of H plus really quickly. So at this point, we ignore the salt's contribution. That means you basically have the H plus concentration, and that means you basically have the pH if you put it in your calculator correctly. Yes, and you should get here, obviously, an acidic calculation. Any questions on that one? So really, this titration curve and the one we talked about last time and a little bit here at the beginning are pretty much identical to each other. They're just sort of running opposite in terms of pH. One's going from a low pH to a high pH. One's going from high pH to a low pH. They have basically the exact same 4 expectations in terms of what you should get in these titrations. So once again, just like we saw with the weak acid strong base, before you begin, you actually have a weak base, so just a regular KB type problem. Before the equivalence point, you need 1 ice table to basically get your buffer, which you should always hit at that point. And again, you could go into your Henderson-Hasselbalch. The difference is, in this case, you most likely will have a basic buffer rather than an acidic buffer in the weak acid one. Same thing here at the equivalence point. You're going to hit a salt that will go through hydrolysis. The difference here is this salt will actually produce H3O plus and make it acidic, as opposed to the previous salt that will make it basic. And lastly, here's same idea. You're just adding more acid at this point, which means it's a strong acid. You just need to get the H plus concentration, similar to what you do in the previous titration curve, where you figure out how much of that strong base you're adding at this point. So once again, as we talked about with these titration curves and problems, it's really good to know where you are in the titration curve, because as I mentioned before you do the calculation, you actually should know kind of what the outcome should be. You should know what type of calculation you're doing before you do it. And that helps us hopefully some indecision of, should I be doing this, if you just jump in. Any questions on that there? All right, well then, it's Thursday. Okay, so hopefully you made some progress into some parts of this, but since we're getting to the end here, let's start going through it here together so everybody's hopefully on the same page. So Here we have several points along a titration curve that we're looking for the pH. As I might have mentioned last time, when you have a problem like this, what we assume is each of these sort of questions are usually just you start at 0 and open it up to that point and stop, and then you start at 0 and open up to the next point and stop. It's not sort of a continuation of volume from one point to the next, unless the problem explicitly says that's what's going on. So in this particular case, we have 100 milliliters of 0.1 molar nitrous acid titrated with 0.1 molar of sodium hydroxide. I do see a Ka value here, so that automatically tells me this is a weak acid, and we know that this is a strong base. So we do have our weak acid strong base titration. And again, we're here taking the sodium hydroxide here and adding it to our acid in this case. That means our titration curve should look something like that, perhaps, with an equivalence point maybe up there-ish along the way. All right, so starting out the first part there, obviously before we begin, we have really just the weak acid in our beaker. So that is what we're going to do. So at point A there is just the HNO2, and that was 100 milliliters, I believe, of 0.1 molar. So it will just be a weak acid dissociation. So we're going to take our weak acid, we're going to break it apart into H plus and a little NO2 minus here. We can do this ice table with the original molarity as we have not added anything at this point. So this is just a regular Ka type of problem happening here. Minus X plus X plus X. That means at equilibrium 0.1 minus X, X, and X. Any questions up to there? Going to go into our Ka expression, which is again our products divided by our reactants. And that's going to give us x squared divided by 0.1 minus x. And that's going to equal our Ka value of 4.5 times 10 to the minus 4. That is a small k value, so you could assume that x is equal to 0. And because you are professionals, you know that is a bad one at like 6.7%. So that is not going to work for you. If you didn't check that, by the way, it's a bad assumption in case you didn't check it. So we're going to go back and solve it our other favorite way, which is the quadratic. So we're going to multiply that to the other side. And that's going to give us x squared is equal to 0.000045 minus, I'm going to go underneath since I ran out of room there, 4.5 times 10 to the minus 4x, bringing everybody to one side. Going to give us x squared plus 4.5 times 10 to the minus 4x minus 0.000045 equals 0. That is our A, B, and C for our quadratic. Putting that into our quadratic gives us x is equal to minus 4.5 times 10 to the minus 4 plus or minus. If you do everything in the square root, inside the square root, I think you end up with 0.000180. And then if you take the square root of that, 0.01342, I think is what you end up with. That's going to be divided by 2, as that's 2 times A, which is 1 in this case. That's going to give us our 2x values. We get an x that's equal to 0.006485 going the plus way. Going the minus way gives us a negative 0.006935. As you could probably guess here, since h plus equals x, the negative is not going to work very well for us here. So it does need to be the positive guy. So that would be our molarity for our H plus. Any questions on that there? That means really that is all we need to go into our pH here. So our pH will be negative log of 0.006485. There it is. And that's going to give us an opening pH here on our titration curve of 2.19. Yeah. Any questions on that? So just a good little reminder that you should check your assumption, although you probably wouldn't have been too far off if you did the assumption, just kind of blew by it, but make sure you do check it. Any questions on that one? All right, so in part B, we're obviously starting our titration. So we want to know what is the pH after we add 80 milliliters of our sodium hydroxide. So let's take a look at that. So B, 80 milliliters of our 0.1 molar sodium hydroxide to our 100 milliliters of our 0.1 molar nitrous acid here. So obviously here we're definitely doing our titration, so we need some moles. So we're going to do a 0.08 times 0.1, and that is going to give us our moles for our sodium hydroxide here. 0.008 moles of sodium hydroxide. We'll go 0.1 liters times the molarity of our acid. And that's going to get us our moles of our acid, 0.01 moles of our nitrous acid. We're ready to go into our equation here. So a little HNO2 plus some sodium hydroxide, your acid-base reaction, gonna give us some water here and a little sodium nitrite happening. Initially here we have 0.01 moles, we have 0.008 moles, and we have 0. So once again, I am starting here, I am adding here. Am I before, at, or after the equivalence point? I am before. And I know that also because the next question asks what is it at the equivalence point, so clearly I'm not there. But again, what we're adding is less than what we started with, so we know we are before the equivalence point. That again should give you a pretty good idea where we should end up with this calculation. Let's see if we do end up there. That means that the sodium hydroxide is going to be the limiting reagent. And that means when we do reach equilibrium here for our nitrous acid, 0.01 minus 0.008, 0.002 moles. We'll have 0 of that and 0.008 moles of this guy here. We do want our total volume at this point. So we started with 100 milliliters of the acid. We added 80 milliliters of the base. That gives us 180 milliliters of total volume at this point. We're going to convert that into liters, which would be 0.18 liters divided by 1,000, right? And we're going to convert these guys back into molarity here. And that's going to get us 0.0111. I like the number. Let's see. And a matching nice number over here, 0.0444. Again, if we look as we should hopefully have expected when we begin with, we got nitrous acid, we got sodium nitrite. Those two things are that is a buffer like we would expect in this titration before the equivalence point. That means that we can go into our Henderson-Hasselbalch at this point, and perhaps we need a pKa value as well would be good. So pKa equals minus the log of the Ka, 4.5 times 10 to the minus 4. Looks like a 3, you call it 335, 3.35 plus the log of our base. Once again, it is the salt that's our base, so we're going to go 0.0444 divided by 0.0111. If I punch it in, that would be better. There we go. There we go. And a 335. That's going to get us there a 3.95 pH in this case at this point in the titration. Any questions on any of those steps there? All right, off to the next part, which is the equivalence point here. In this case, they did not give us the volume to reach the equivalence point, so we might need to figure that out for our calculation purposes. There are a couple ways you could do that. We know, for example, actually, we'll do it as we come over here. So in part C, at the equivalence point, we again have our 100 milliliters of 0.1 molar nitrous acid. And we're adding our 0.1 molar sodium hydroxide. So we will get our reaction like we had in the previous step there. And we will also have, just like in the previous step, our initial moles of our acid here, which was 0.01 moles. So we'll borrow that, 0.01 moles. That is what I'm starting with. This is what I'm adding. And I know because this is the equivalence point, one way you can figure out things is I know the moles of sodium hydroxide should be the exact same number, right? Which means now that I know the moles and I know the molarity, I'll do it right here by water. Molarity is moles per liter. I know the moles, I know the molarity. I can take the moles divided by the molarity and figure out the volume in liters. And if I did that, liters would be my moles, which is 0.01 divided by my molarity, moles per liter. And those guys are going to cancel out there, hopefully. And that's going to give me 0.1 liters, which is the volume needed to reach the equivalence point. That's 100 milliliters, right? If you times it by 1,000. Also, I could have done M1V1 equals M2V2, where this could have been 0.1 and 100, and 0.1 there gives you 100 milliliters there. Yeah, so again, there's a couple different ways that you could have got to that information. Any questions on that there? Now that I scribbled in the spot I need, let me erase that little spot right there, I think. All right. All right, so we figured out there that we should have 100 milliliters to reach the equivalence point. All right, continuing on with our table here, this would be 0. Once again, you can't choose, hopefully, the wrong number. That's going to be the only number on the board, pretty much, 0.01 all the way across here. And that's going to give us 0, 0 like we would expect, 0.01 moles. Now we know we needed 100 to get there of this guy. And we started with 100, so that's a total volume at this point of 200 divided by 0.2 liters. So that's going to give us 0.01 divided by 0.2. That's going to give us a molarity of 0.05 molar in this case. First off, any questions on that there? We are going to go a little long here just to finish this example so we can put it in the books. What we do have left with at this point is a salt, right? And that salt is basically sodium ion and a nitrite ion. We do not need to worry about that guy, right? Because it is a neutral salt. How about the NO2 minus? Do we need to worry about it? We do, because we know in this titration, bless you, that salt is going to go through hydrolysis, right? So it came from a weak acid, which means it's going to act as a base when it reacts with water. So this is the point in titration curve where you need a second ice table. And obviously it does not have an H to give. So that also hopefully helps you make your decision correctly here. It's got to accept, and it will make where it came from, and it will make a little hydroxide action here. And once again, we should expect our pH here now to be basic. And we also need a KB, right? And we have a Ka in this case. So might as well take care of that right here while we're thinking about it. So Ka will be 1 times 10 to the minus 14 divided, I'm sorry, KB will be 1 times 10 to the minus 14 divided by our Ka value, 4.5 times 10 to the minus 4. We're going to go like a 2.2 times 10 to the minus 11. So that's going to be good to use here. Remember, the whole purpose of the first ice table there is to get that guy's concentration. So now we could put it in 0.05. This again is going to be molarity and x's as we go through it, plus x, 0.05 minus x, x, and x. Once again, we are going into our KB here, products over reactants, which would give us x squared divided by 0.05 minus x is equal to our KB value of 2.2 times 10 to the minus 11. I think I'll flip a page here. So x squared 0.05 equals 2.2 times 10 to the minus 11. We're going to assume x is equal to 0 and hope a lot that it works. I think we should be all right. We're going to get rid of that x, remember? So that's going to give us x squared divided by 0.05 is equal to 2.2 times 10 to the minus 11. We're going to multiply followed by a square root there. So that's going to give us times 0.05, a little square root action. That's a lot of zeros at this hour. All right. I'm going to go scientific notation. That's going to give us an x is equal to 1.05 times 10 to the minus 6. We do want to check it, so we're going to divide it by 0.05 times it by 100%. And like I said, I think we should be all okay on that. We're not even like 0.1%. So the check is good in this case. So that x value is, if we go back to our table, the hydroxide concentration. So that's, again, an important thing to remember. So we do need to calculate here the POH. So the POH is equal to negative log of 1.05 times 10 to the minus 6. And that is going to get us here a POH of 5.98. That's going to get us a pH when we subtract 14 of 8.02, which is basic and what we would expect in this particular case. Any questions on that there? All right, last part of the titration problem here, which is part D. We can't just leave one left over here. So when we add 105 milliliters of our base, so let's get that one here. So we are obviously at this point past the equivalence point, 105 milliliters of our 0.1 molar sodium hydroxide to our 100 milliliters of our 0.1 molar HNO2. So once again, obviously here we're going to get our equation. And obviously here we are going to do some moles, right? So that's what we're starting with. This is what we're adding. And we have our 0.01 moles. 0.105 times 0.1 gives us 0.0105 moles of this guy and 0. So obviously we are past the equivalence point as we talked about, since we just did the equivalence point. But once again, we have more moles of what we're adding than what we started with. That means at this point it is going to be our acid that's the limiting reagent. 0.01 moles minus 0.01 moles. Again, we want to take the smaller number for sure. That's going to give us 0, and we will end up with there 0.0005 moles and 0.01 moles here. Our final volume here at this point, 105 and 100 is a total volume of 205 milliliters. So we're going to convert back into molarity by dividing by 0.205 liters. So if we do that, 0.205 there, 0.00244. For our other one there, we end up with 0.0488. We are left over at this point with these two things. Is that a buffer? No. Again, we have our salt like we expect at this point, which is a base. We have our strong base, which is much stronger base. So we don't really care all that much about that. That means that we then have the hydroxide concentration into our POH. That's going to give us a POH of 2.61, and that will get us our pH of hopefully basic 1139, which definitely is basic in this case. So hopefully we saw there it went up as we're doing our titration. Any questions on that there? All right, so that pretty much